Okay, in this video we're actually going to go back to something we studied earlier in the semester with composition of functions. But just as a quick review, if we recall, if I had something like f of x equals x squared, g of x is 2x plus 1, then I can do f circle g of x, f composed with g of x. And in this case, that's f of g of x, which is f of, we replace g of x with what g of x is, which is 2x plus 1. Now I apply f to that. F takes whatever I plug in and squares it, so I get 2x plus 1 squared. We're going to work a little bit more with that, so I just want to quickly make sure we remember what it was. But for the purposes of this, suppose we have f of x equals 2x plus 3 and g of x equals x minus 3 divided by 2. We want to do the composition of those two. So if I do it really quickly, we'll do f circle g of x, which by definition is f of g of x, which is f of, I replace g of x with what g of x is, which is x minus 3 over 2. Now I take f of that. F takes whatever I plug in, x minus 3 over 2, multiplies it by 2, and then adds 3. And now if I simplify this algebraically, here the 2's will cancel, and I'll get x minus 3 plus 3. Now the 3's will cancel, and I get x. Which essentially means I started this problem by plugging in x, and after applying both functions, I ended with x, which is actually where I started. If I look at the other composition, g composed with f of x, I can do the exact same thing. That's g of f of x, which is g of, replace f of x with what f of x is, 2x plus 3. And then g takes whatever I plug in, 2x plus 3, subtracts 3 from it, and then divides 2. Here, plus 3 minus 3 will cancel, and I'm left with 2x over 2. The 2's will cancel, and I get x. And again, I started with x, I applied both functions, and I ended with x, which is back where I started. Essentially, the idea here is, in this case, when that happens, I really have a set over here, call it x, and then I apply a function to it, and I end up over here at y. So say I apply f that goes from x to y. Now I apply g, but g really takes the y I got and sends it right back to x where I started. This doesn't happen all the time, but when it does, we actually give these functions special names, or in particular, we give g a special name. We say g is the inverse of x. Essentially, g undoes x. And when we do that, the notation we use is g equals f to the negative 1 of x. That's not f raised to a power, it's just a notation, but it just means inverse. They undo each other. F goes here, f inverse goes backwards. With a little bit of kind of thought about this and understanding, you can see some inverses pretty quickly. If I say f of x equals x squared, g of x equals square root of x. Now if I do f circle g of x, that's f of the square root of x. That's the square root of x squared. The square root square cancels, and I'm left with x. I could obviously also do the same with the cube and the cube root and things like that. But the idea is we have a lot of functions, and some of them will have these inverses. There is actually a trick to determine if a function has an inverse or not. And it is important that the way to determine if something has an inverse or not, we'll mention it really quickly. It's what's called one-to-one or one-to-one functions. I'm going to write the mathematical definition, but we're not really going to use it in this class. We're going to use another way to determine this. But essentially, if f of x1 equals f of x2, then x1 equals x2. That's the mathematical definition of one-to-one functions. The idea, from a graphical perspective, it makes more sense. Say we have the quadratic, the parabola. I'm going to pick 2 points on that parabola. We'll say -1 and 1. So that's the point 1, 1. That's the point -1, 1. Now in this case, f of -1 is equal to 1. F of 1 is equal to 1. So f of x1 equals f of x2. But in this case, x1 and x2 are not the same. -1 doesn't equal +1. Which means this function is not one-to-one. If it was, anytime you have 2 points that have the same function value, they have to be the same point, which seems bizarre, but if we look at another graph, we'll go with the cubic function. Now, if I again look at 1, 1, in order for it to be one-to-one, every point that gives me the function value 1 has to be that 1 point right there. But it's pretty clear there's no other points here that give me 1. There were 2 points that gave me 1 here. There's only 1 here, which means this is one-to-one. This is not one-to-one. The algebra that is important from a math perspective, and being able to algebraically show functions are one-to-one is important. For the purposes of this class, though, we're actually going to simplify that. When we were talking about functions earlier, we had the VLT, the vertical line test, to determine if something was a function. If something touches your graph more than one, if a vertical line touches your graph more than once, it's not a function. We actually have a similar test for one-to-one functions, the HLT, the horizontal line test. And it actually works the exact same. If a horizontal line touches your graph more than once, it's not one-to-one. So right here, I can draw a horizontal line right here, touches the graph more than once, that's not one-to-one. Over here, every horizontal line I draw only touches the graph once, it is one-to-one. So, for the purposes of this class, all we really need to understand is the horizontal line test. We're not going to worry about the algebra of one-to-one functions. But as it goes, the only functions that can have inverses are functions that are one-to-one. Admittedly, we just said that if f of x equals x squared, then the inverse of that is the square root of x. And x squared is not one-to-one, but we can do this trick where I take a function, like the parabola, and I say, that's not one-to-one, it fails the horizontal line test, but if I restrict my domain from a real-world perspective, if I only look at the x's greater than or equal to 0, now that function is one-to-one. Now it will pass the horizontal line test. So for some functions that aren't one-to-one, we can do little tricks like that, restricting our domain. We don't really need to worry about that much with what we're doing. We just want to have a general idea of what one-to-one means. And I'll also point out, for the most part, we only care about, for the rest of this semester, functions that have inverses. We'll see why in a few minutes. But if you need to be one-to-one to have an inverse, and we only care about functions that have inverses, then essentially all the functions we're going to look at will be one-to-one. so that we can find their inverses and do things with them. So, just really quickly, suppose I have f of x equals x plus 2 and g of x equals x squared. I want to know if they're inverses. We know that they're not. But all I have to do is always look at the composition. F circle g of x. If I do that here, that's f of g of x, which is f of x squared, which is x squared plus 2. And the rule says they are inverses if I start with x and I end with x. That's not x, they're not inverses. But then the question becomes, if I have a function, say f of x equals x plus 3 over 2, that's the equation of a line. It is a one-to-one function. It should have an inverse. Can I actually find it? And algebraically, there's a trick. What I do is, I rewrite f of x as y, so y equals x plus 3 over 2. Now, essentially what an inverse does is flip your x and your y around. You start with x, you go to y, then you go from y back to x. So algebraically, you flip your x and your y. Y equals x plus 3 over 2. Write it as x equals y plus 3 over 2. Now just solve that for y. So multiply the 2. 2x equals y plus 3. Subtract the 3. Y equals 2x minus 3. That's a function, and that should be my inverse. F inverse of x is 2x minus 3. If I check it really quickly, f composed with f inverse of x is equal to f of 2x minus 3, which is, let's see, 2x minus 3 plus 3 divided by 2. Just plug this into that. Minus 3 plus 3 cancels. I get 2x over 2. The 2's cancel, and I get x. So I started with x, I ended with x. They're inverses. Just really quickly, I want to do one more before I finish this video. I'm almost out of time. So we can make sure we're good with the algebra. So suppose I have f of x equals 3x plus 6. That's a line, it's one-to-one, so to find the inverse, I rewrite it as y equals 3x plus 6. Now I flip my x and my y. X equals 3y plus 6. Now I solve for y. Subtract the 6. X minus 6 equals 3y. Divide the 3. Y equals x minus 6 over 3. And that should be the inverse. I'm not actually going to do the algebra for this one, but if you think about it, this function multiplies by 3 and adds 6. This function subtracts 6 and divides by 3. It seems like the exact opposite, so it will work. It's doing the exact same operations in reverse. As far as it goes, you guys need to be able to understand what a one-to-one function is, horizontal line test, and then given two functions, determine if they're inverses by looking at the composition. And then if necessary, given a function, find its inverse using this little xy trick right here.